Hello, sir. Sir, is it okay? We can start now?
Yes.
I would, first of all, it is my privilege to welcome all to this chemistry webinar on the topic of NMR Spectroscopy, Basic Introduction to Structural Determination. And we are very thankful to Professor Devan Singh Rawat, who has agreed to give us this webinar. And he is one of very prominent organic chemist who has a vast experience in spectroscopic studies from University of Delhi. And I thank you, sir, first of all, on the behalf of Department of Chemistry. And I would request Professor K.N. Singh, Chairman, Department of the Chemistry, to kindly officially initiate this webinar series. Professor Singh.
Good morning, participant. I welcome you all in the chemistry webinar under the aegis of Eureka Lecture Series, organized by the Chemistry Department, Punjab University, Chandigarh. The first speaker in this series, Professor D.S. Rawat, FRSC, CChem London, Department of Chemistry, University of Delhi. The topic of his talk is NMR Spectroscopy, Basic Introduction to Structure Determination. Professor Rawat obtained his master's degree from the Kumaon University, Nainital in 1993 and PhD in medicinal chemistry from CDRI, Lucknow. Professor Rawat started his career as an assistant professor in medicinal chemistry at National Institute of Pharmaceutical Education and Research, NIPER, Mohali, and shifted to University of Delhi in 2003 as associate professor and promoted to full professor in 2010. His research interest lies in the area of development of small organic molecules as anti-cancer, anti-malarial, antimicrobial, anti-Parkinson agent, and nanocatalyst. Professor Rawat has published more than 148 research papers, authored a book, 3-book chapter, 9 patents to his credit, and have a citation index greater than 5,000 and H index of 42. Professor Rawat has supervised 20 PhD students. Professor Rawat is an associate editor of Nature Scientific Report, RSC Advances, International Journal of Drug Discovery. He served as a guest editor of Anti-Cancer Agent in Medicinal Chemistry and Current Protein and Peptide Science. Professor Rawat is a recipient of CRSI Young Scientist Award 2007, ISCB Young Scientist Award 2010, Professor D.P. Chakrabarty's 16th birthday anniversary award 2007, Professor R.C. Saha Memorial Lecture Award, Indian Science Congress 2015, and he is a visiting professor, Japan Advanced Institute of Science and Technology, Japan. He is a fellow of Royal Society of Chemistry and CChem London. And on behalf of the chemistry department, I welcome Professor Rawat for sparing time from his busy schedule for this webinar lecture. So again, I welcome Professor Rawat for this talk.
So with this, I would like request Professor Rawat to kindly take over, and you can decide, sir, whatever way you want to go. If you want to have questions in between, we can ask students to raise hands, or you can have towards the end. It is totally up to you, sir.
I think towards the end will be better.
Fine, sir.
At the end.
Fine, sir. Fine.
Yeah.
So you can share the content of your PPT.
Okay. Thank you.
हॅलो कुठे आहेत म्हणलं
Request all the viewers to kindly mute their voices, please.
Yeah. Can you hear me now, Rohit?
Yes, sir. We can.
Okay. Okay. Thank you, Professor Singh and Dr. Rohit, for your invitation and kind word of introduction. You know, this is a very clear precision for all of us. We are used to interact with the students a large number, deliver a talk, and this is where, you know, you don't have an audience in front of you and you have to speak, and it's really, really tough job. So most of the time ये ऐसा होता है जैसे शायर होता है, शायर को जब तक कोई सुनने वाला न हो तो तब तक उसको मजा नहीं आता है, तो वैसा ही हम लोगों का भी होता है, टीचर्स का भी. But this is the new way of delivering talks, and I hope I'll be able to do the justice. But in NMR, when we talk NMR, 1 hour talk is nothing in NMR, so it means I have to skip so many things in between. And this talk I have made in such a way that the beginner can understand where people make a small kind of mistakes, and they can understand all those principles. Let me go with this. See why spectroscopy is so important, or why is structure. So whenever we talk about chemistry, chemistry cannot be taught without structure. That's the biggest problem. So the first example I would like to give you about the structure. You know, all of us know that Lewell and Van 't Hoff talked about tetrahedral carbon way back in 1874. And one of them was 22-year-old and another was 27-year-old. And both work in the lab of Kaprlus, who discovered the structure of benzene. And they published their result about tetrahedral carbon. And this observation or this research was heavily criticized by one of the topmost chemists of that time called Hermann Kolbe. And he termed this piece of paper as childish fantasy. From 1874 till 1957, nobody realized the importance of the asymmetric carbon in the biological system. The first time that was realized in 1957 when the drug called thalidomide was introduced in the clinical market by the German company called Grünther. And this drug was prescribed to the pregnant women for the treatment of their morning sickness. After 6-7 years, when data were collected, the data was very catastrophic in a sense that more than 10,000 babies died, and those survived had a permanent disability like this. As a chemist, if you look at this structure right here now, it has a chiral center here, so it means it can have 2 enantiomers. So when this drug was developed as a racemic mixture. So one of the structure was effective enantiomer, another was a mutagenic, had a mutagenic issue. So this is why structures are very important. Without the spectroscopy, what was the life of a chemist? So if you look at it, this is the structure of camphor, and the molecular formula of camphor was determined in 1833, and structure determination took 30 years in 1863. Why this so? Because only diffusion method was available at that time. There was no spectroscopy technique available, so it took 30 years. Now, today, the structure of mycotoxin, which is one of the biggest natural product apart from biomolecules, within 5 years, the structure of this molecule was established. That was made possible because you have spectroscopic techniques at your disposal now as a chemist. And today what I'm going to talk about one of the spectroscopic technique that is called nuclear magnetic resonance spectroscopy. So whenever we talk in organic spectroscopy class, we talk about NMR. And when we talk about NMR, we always tell to the students that what kind of contribution two of the great chemists, Bloch and Purcell, has made, and they developed the NMR spectroscopy the way we use it today. But we don't tell them how many people have received Nobel Prize on this particular technique. There are 8 people who got Nobel Prize for the development of NMR. First to be Otto Stern and Sudar Rabi in physics, then Bloch and Purcell in chemistry, Ernst in chemistry, high resolution NMR, then 3-dimensional structure of macromolecules by Ulrich, and the last one in 2003, the Nobel Prize was given for the development of MRI. And you know, MRI was based on the discovery that was made by Rabi in 1944. He got a Nobel Prize on that. And at the end of his life, he suffered from a cancer, and his cancer was detected by MRI. And when it was done, what he said, I saw myself in that machine. I never thought my work would come to this. So Ravi, on seeing a distorted image of his face inside the MRI machine. Beautiful work that was done by Bloch and Purcell, we all know that. Do you know how they published the paper? Both of them published two research papers on the same journal, one after another issue, in the same year, 1946. What was that? This was the paper. Bloch said it is a nuclear induction, and Edward Purcell said it's a resonance. So NMR, the terminology what we use, was given by Purcell. And physicists today even, they don't use resonance. They talk about induction, nuclear induction. So the FID, free induction decay, is after the name of this discovery. What was the size of that paper? If you see, the full size of paper is half a page. From Bloch and Purcell, about a page. So two papers, half a page and one page paper, gave a Nobel Prize to these two gentlemen in 1952. In fact, after they published their results, they talked among themselves, then they realized both of them have a complementary findings on the same subject. That's how it was. So what NMR gives you the information? NMR gives you the information. It allows to determine the connectivity, stereochemistry, conformation. You can study the molecular dynamics. So whenever we talk NMR, the students make nowadays, we have the WhatsApp language. So we talk PMR, CMR, all that, but that's wrong. You should not say that. It is a nuclear magnetic resonance. That's the terminology. So which nuclei you are adding, you should add it first. So when you talk about proton NMR, so it should be 1H NMR, not PMR or CMR. So let's make one thing clear first what we are talking here. We are talking here about the magnetic property of a nucleus. Magnetic property of a nucleus. This nucleus can be of any atom, right? So when we talk the magnetic property of the nucleus is composed of proton and neutron, right? And nucleus has the intrinsic quantum property of spin, and overall spin of a nucleus is determined by a spin quantum number I. Okay. So if your number of proton and neutron are same in a nuclei, spin quantum number is 0. So any atom that has a spin quantum number 0 is NMR inactive. Okay. So it means what? It means, I have summarized this in this slide. So this is your atom. This is atomic weight, atomic number. If both atomic number and atomic weight are even, you have I is equal to 0. So this is called NMR inactive nuclei. Carbon 12, oxygen 16, sulfur 32. But if you have odd atomic number or even and odd molecular weight, this is NMR active. The spin quantum number is half integer. So that in that category you have a hydrogen, you have a carbon 13, nitrogen 15, fluorine 19, so and so forth. And another one is atomic weight even, atomic number odd. In that case, the spin quantum number is 1, 2, 3 like that, and you have a nuclei. So only nuclei which has this kind of combination is NMR inactive from the periodic table. So it means you can study each of the atoms present in the periodic table by NMR except those which have net spin quantum number 0. So when we talk about the magnetic property of a nucleus, nucleus is a positive charge, right? So it has a charge and it has a spin. So anything that is a spinning particle has a charge will behave like a bar magnet, right? So if it behaves like a bar magnet, what is the magnitude and direction of that magnetic field is determined by a vector called magnetic moment. Okay? And in absence of any applied magnetic field, if I talk about the proton, the magnetic moment of proton is oriented in all directions, random orientation. But if you place this in an applied magnetic field, it adopts two orientation now. One goes parallel with the applied magnetic field and oppose against the magnetic field. So that gives you kind of a transition between lower energy state and higher energy state. This is what it happens. So you have opposition and you have a parallel. Okay, and the biggest problem is the population between higher energy state and lower energy state is very, very small, and that small population gives you the NMR signal. And if the population of the excited state and the ground state, the lower spin state, the higher spin state is equal, we call it as saturation. In NMR, you won't see the NMR signal. So this is what it happens when you apply a magnetic field. You get the high spin state, that is minus half, low spin state plus half. And in NMR, we have two very important concepts. One is shielding, deshielding, another is equivalent and non-equivalent proton. And both of these can be explained based on the chemistry knowledge what we have from class 2 level. I will explain this how. Now look at this acetophenone. Okay, if you draw the resonating structure of acetophenone, you have a plus charge at second and you have plus charge in fourth position, right? So what I said when we talk about NMR, in the proton, okay, this proton has a nucleus, right? And proton is attached by a covalent bond with the carbon. So it means it has a bonding pair electron. So this bonding pair electron circulates like this. So the bonding pair electron is far away from the nucleus or close to the nucleus. That forms the basis of shielding, deshielding. In other terms, what we explain it, the circulating electron generates a secondary induced magnetic field under the influence of applied magnetic field, and that can be parallel or opposition to the applied magnetic field that causes shielding and deshielding. But the best example to understand that is based on the electron density around these nucleuses. So if you look at it, the second position and fourth position, you have positive charge. So it means the electron density is smaller at this position, at this position. So electron density less means what? Deshielding. Deshielding means high delta value. And electron density at 3 and 5 position is higher because there is no positive charge. So it means what should be the order of chemical shift in that case? H2, S6, H3, H5, H4. And look at it. You see the same order. This is how you can understand the shielding, deshielding. What are the factors that affect the chemical shift? These are the broadly 4 factors that affect the chemical shift. Let me give you the example of electronegativity first. If you look at the electronegativity chart from chlorine to iodine, and this is the range, okay, it decreases. So electron negative means what? This fluorine pulls the bonding pair electron towards itself. So what happens? The electron density at this position is decreased. Decrease means deshielding. Deshielding means high delta value. Look at it here. It goes like that. So it means the electronegativity concept makes a perfect sense about shielding and deshielding. That's true. Let's take this example now. What it says, you have acetonitrile and methyl chloride. CN is more electronegative than Cl. So it means based on this reasoning, what I talked to you right now, this CS3 of CN should have been more deshielded, downfield, high delta value, but it is not. It is something else. So it means there may be other factors also which affects the chemical shift values apart from electronegativity that I will come a bit later. Now, in chemistry, what we we say methyl is electron donating. Okay, if it is electron donating group, what would happen? Electron density around this CH would be much more in comparison to this. So more electron density means shielding. Shielding means upfield, low delta value. So this should have a lowest delta value and this should have a highest delta value. Is that correct? No. So what is then? What's the problem? Problem is this. This is because carbon is more electronegative than hydrogen, hence CH attached with 3 CH3 groups is more deshielded and downfusion. Another concept what we talk about is said that as character of carbon atom increases, the electron cloud is more closer to the carbon. So if electron cloud is more closer to the carbon, it means hydrogen will have lesser electron density. So less electron density means deshielding. Deshielding means high delta value. So if that is correct, this should have been most deshielded than this. But that's not correct. This is what the order is. This means what? This suggests that there are other factors which affects the shielding and deshielding in NMR apart from electronegativity and S character of a system. What are those? This is called magnetic anisotropy. Magnetic anisotropy is nothing but if any measurement you want to take, if it varies with the direction in which you want to take it, is called magnetic anisotropy. So mostly in case of pi systems, the molecule adopts one particular conformation, and that leads to the shielding and deshielding in that particular compound. If you look at the benzene is a planar like this, and you have an applied magnetic field over here. So this side like this will be the induced magnetic field. So this side of the molecule right here is in the deshielded region, and if something comes on the top of the benzene ring like this, that one will be shielded. Okay, and in case of aldehydes, it goes like this. So this hydrogen is deshielded. So aldehyde hydrogen comes around 9 to 10 ppm. So that is because of electronegativity of oxygen and anisotropy of C double bond. Similarly, you have alkene. Alkene hydrogens are in deshielded region, and alkyne adopts this kind of conformation actually. So the CH is in the shielded region. If you look at it, the best example is the paracyclophene, in which one of the hydrogen of the benzene ring comes on the top of the other benzene ring, and this region right here is the shielded core. As a result, benzene proton appears at 4.17 ppm. Otherwise, benzene protons comes after 5 ppm. Why nitrile versus chloroethane? This is what it is. So, yeah. So the methyl group falls in the shielded cone. This is why it is more shielded in comparison to methyl chloride. Most of the time when we talk about anisotropy, we talk about the pi system and a cyclohexane system, and we stop it there. It's not like that. Cyclopropane has a biggest anisotropic effect because it is very rigid molecule, and the cone which it generates, it affects the chemical shift to the nearby protons. If you look at this Norbornene system here, this is 3.99 ppm. And if this position is attached with a cyclopropane ring, now you see the shielding. And if the geometry of this is to this side, and this is 4.24. And cyclohexane we all know. And similarly, in the cyclohexane system, 5.70, it comes 4.95. So that also affects the chemical shift. This is called cyclopropane anisotropy. So whenever we talk about NMR, the biggest thing is the equivalent and non-equivalent proton. And in the net examination, this is one of the questions most of the time people ask, and unfortunately most of the students attempt it wrong. How to understand whether a given system has equivalent and non-equivalent. There are three tests actually for that. Number one is what we call homotopic, another called enantiotopic, the third one is diastereotopic. So in case of homotopic, you have the butene system. Okay, you substitute either of these two hydrogens by any letter you want, D, Br, Cl, whatever it is. So I substitute this by D, and this one also D. If you look at these two compounds, what is the nomenclature of these two compounds? Nomenclature remains same. So it means these two CH are homotopic, and homotopic protons are equivalent. Similarly, enantiotopic protons are those protons which you substitute imaginarily and become a chiral center, and enantiotopic protons are chemically as well as magnetically equivalent. But what about diastereotopic protons? So this is one problem in the textbooks. Actually, what it is written in many of the textbooks, that methylene next to chiral center is diastereotopic, and for that the example of 1,2-dichloropropane is given. Okay, and unfortunately that's not a right statement. The diastereotopicity can go up to 7 bonds. Okay, it's a diastereotopic group, nothing to do with the hydrogen. That's why I have given you example here of valine. Okay, if you look at valine here, you have a chiral center here. Now see whether this methyl and this methyl are equivalent or non-equivalent. Do the replacement test. Replace one of the methyl by X. What happens? When you substitute this center also become a chiral center. How many chiral centers now? 2. It means these two methyl groups are diastereotopic. Remember, diastereotopic groups are chemically as well as magnetically non-equivalent. So we'll give you different signals. Now, if you look at NMR spectrum, this valine, how it looks like? It looks like this. This one, the left-hand side, this is the CH here, isopropyl. I have not given this complete spectrum here. I just wanted to show you something. So if you look at this NMR spectrum, most of the PhD students make a mistake here. They will write it as a doublet. Okay, please remember, when you have a chiral system, you have a chiral center in your molecule in your isopropyl group, expand the isopropyl region. If you expand this isopropyl region, I did in this case 0.96 to 0.1045. What is in there? 2 doublets. So most of the time you make a mistake, you write what? Doublets of 6 protons. That's it. No, it's not correct. So 2 doublets of 3 protons each. Again, I have another system here. You have a vinylic system. You have a nitro. This is the CH2. Rest of are CH. And do the substitution test to see if these are equivalent or non-equivalent. C7 and C8 substitute by Br, let us suppose. If you do this, this becomes trans, this becomes cis. So it means what? These are not homotopic. So it means these two are non-equivalent. This is a vinylic proton. S6 is totally different. Now go to H1 and H5. H5 is in between the vinylic group and a nitro is different. H1 is different. What about H2 and H3? Do the same substitution test. Substitute by Br, substitute by Br. What do you get? You get 2 different compounds. Do the nomenclature of it. Different compound. It means these 2 hydrogens are non-equivalent hydrogens. And in the case of diastereotopicity, symmetry plays an important role. If you look at this molecule right here, it is a achiral molecule. Okay, so if you do the substitution test in this molecule, these CH2, whether these CH2s are equivalent or non-equivalent, substitute one of the H1 by X, let us suppose. Since this is a symmetrical molecule, this half is equivalent to this half. Okay, this half is equivalent to this half. So if you do that, substitute this by X, this become a chiral center, this become a chiral center. So it means these 2 hydrogens are diastereotopic. So how many non-equivalent protons there? 1, 2, 3, 4, 5. Okay. Now look at another example. You have this molecule here, right? You have a chiral center here, you have a chiral center here, and you have a CH2. These CH2s are equivalent or non-equivalent. This has C2 axis of rotation. Remember, the group which you are determining or equivalent or non-equivalent or diisotopic or not, try to find out whether there is C2 axis of symmetry or not. If it has a C2 axis of symmetry, these will become equivalent. So it means in this case you have 1, 2, 3 and 4. This is not diisotope. These are equivalent. And the beautiful example I will show you in this case now is the citric acid. If you do the citric acid also, it has a plane of symmetry, non-chiral molecule. And if you do the substitution test, this HA or HB, which generate a chiral center, this become a diisotope. To understand whether the group is diisotopic or not, the best thing is to draw the Newman projection formula. If you draw the Newman projection formula of citric acid, what you found here, HA and HB are in totally different environment. Okay, if they are in totally different environment, it means they will couple to each other. That is, this is what we call geminal coupling. How the NMR of this looks like? NMR of this looks like this. These two protons gives you a doublet like this, but the doublet is not 1:1, right? You can see it. Intensity of both of these peaks not same. So this is what we call a second order doublet, but you can see the diisotopicity clearly exhibited by these kind of molecules which have a plane of symmetry, but there is no symmetry along with the CH, and that's why diisotopic. Now, if you are asked to calculate the non-equivalent proton in these kind of systems, whenever you are asked to determine the non-equivalent system of protons or the groups in your compound, please remember one thing. As a chemist, you have, yeah, Rohit, you want to ask anything? Hello. So as a chemist, just okay.
No, sir.
So
there was a
yes,
there was a question, a hand raised. So I just replied to that person that you can ask the questions towards the end. That's it.
Yes, ask them to write down the question.
Yeah, you can write down the question in the chat also.
Yeah, thank you. So whenever you are asked to non-equivalent and equivalent protons, please remember one thing. How many type of protons we deal with? We deal with only 3 kind of protons. 1, CH3, CH2, and CH. Okay, when this kind of question is asked to you, what explains what we have, more than 80 to 90%, 97% students attempt it wrongly. The problem is, whenever you are asked to, deduce the non-equivalent number of protons, you look a molecule as a whole. Don't do that. So in this particular molecule right here, what do you have? You have 2 CH3s, right? One CH3 is attached with CH, another is attached with CH2. So it is different. Then you have a CH2 here, you have a CH2 here, you have a CH2 here. And you have a CH2. This CH2 is the vinyl. So this is different. You have a chiral center over here. So this can be a diisotopic, this can be a diisotopic, this can be a diisotopic. And you substitute this can also be a diisotopic. Do that. This is how it looks like. So if you substitute this by X, so it gives you a cis and trans isomer right now here. Okay, this is a diisotopic, this is diisotopic, this is diisotopic. So total 12 non-equivalent protons there. Similarly, you can do this same thing here also. You have 11 non-equivalent proton this system. So what I talked to you to till now is about chemical non-equivalent. Chemical non-equivalent means the chemical shift different. Different group have different chemical shift. This is what we call chemical non-equivalent. There is another term called magnetic non-equivalent. That is really difficult to explain sometimes. So I have tried to make the example very kind of easy going by taking the example of para-nitrochlorobenzene. Now what you do here, this is HA dash, HAB dash, okay? A dash, B dash. HA and HA dash substitute by Br. So when you substitute HA by Br, this is the product. A dash, this is the product. If you want to write the name of these two compounds, what is the name? Nomenclature? It's the same. So it means these are chemical shift equivalent. Now do the same test for HA and HB. Okay. So when you substitute HA by Br, this is the product. When you substitute HB by Br, this is the product. Now, if you want to write the name of these two molecules, the nomenclature is different. So it means these are non-equivalent. What non-equivalent? This is what we call magnetic non-equivalent. If you look at this structure again, HA and HB, this has this relationship with this B, but this HA has different relationship with this HB. So this is what we call magnetic non-equivalent, means J non-equivalent. I'll give you a beautiful example for that. Look at this. Most of the PhD students till 2011, the literature is full of a mistake. What was that? Look at the benzothiazole. You have an X here. X is equal to sulfur or SO2. And if I ask you what will be the multiplicity of this CH2, everybody will answer it's a clear-cut triplet because it has a CH2 next to it. This will be a multiple. Okay, multiple out of subset or whatever. But in 2011, people noticed first time that whatever is reported here for SO2 is wrong. What was it that? This, when SO2 is here, this CH2 looks like this. It is not a triplet. This is also not a triplet because 1:2:1 ratio, it is not there. It is a second order triplet. Why it gives the second order? Sulfur containing compound. If you have oxygen here, it doesn't give you that. If you have a sulfone here, it does. So if you draw the Newman projection for the sulfoxide here, you will realize these two CH2s are magnetically non-equivalent. And that's why they give you complex spectrum. One of the questions what we ask to the students, actually, this is a good question for the teachers also. If you look at the question papers, most of the time we ask you the question, how many signals the following compound will give you in NMR? And this is the most common question. So I will give you the example here. So if this is here 1, 2, 3. So it is 1,2-dichloropropane. Okay, so this is the chiral center. This is CH2. So these are diisotopic. So how many non-equivalent? 1, 2, 3, 4. 4 non-equivalent. How many signals? 1, 2, 3, 4. So how many non-equivalent protons is the right question, or how many signal is the right question? That's the question now. So in this particular example, both questions are correct. I have shown you, right? Let me give you a complex system. Yeah, this is called bisabolol, and this is the structure of bisabolol here, and this is the NMR spectrum. If I ask you to count the number of signals here, how many signals you can count? 1, 2, 3, 4, 5, 6, maybe 7, maybe 8. I don't know how many here. 2 here. Maybe maximum 10 or 11 you can count. You can't count more than that. How many non-equivalent protons are there? You have 17 non-equivalent protons. Remember, non-equivalent proton does not necessarily means you will see those many signals in the NMR spectrum. It all depends whether your NMR spectrum is of first order or second order. If it is a second order, it will be a complex spectra, so you won't be able to count the number of actual number of signals in the spectrum. Another thing we talk about integration value is directly proportional to the number of protons. It is more than 95% chances there you can get right kind of integration value. But if your spectrum is of second order, number one. Number two, if the T1 and T2, the relaxation time is not taken care well by the spectrophotometer person who is recording the spectra, that may not be true. I will show you the example here. In this case, total the integration value comes about 22.59. How many protons there? 19. So don't get confused with these numbers. Okay, so it all depends how good you are in recording your NMR spectrum. It gives you the information. 96, 97% time it will give you correct, but sometimes it may not. If it doesn't give you, you should understand the reason. When we record the NMR spectrum, we give you the solvent always. Why this so? Because the solvent affects the chemical shift values of the protons. Here in this particular case, this region of the molecule is shown here. In benzene, these are the chemical shift values. In CdCl3, this is the chemical shift values, because there is a pi-pi stacking with the benzene with the molecule that you are studying. So this is why there is a chemical shift variation. Concentration does affect the NMR spectrum for the PhD students. Most of the time, when you go and get recorded your proton and carbon NMR, you submit the same sample, right? And this is not correct actually. If you do that, there will be two problems. One, the relaxation time T1 and T2 varies depending on concentration, so the quality of the spectrum will not be good. Number two, if you have heteroatom containing protons, the chemical shift change drastically. So in dilute solution, the hydrogen bonding is minimum, so there is a coupling of the OH also. But in case of the concentrated solution, there will be more hydrogen bonding, so the OH is more deshielded. This is the excellent example of restricted rotation, and that is example of N-dimethylacetamide. So whenever we talk about compounds, we have right here not a single bond, 1.5 bond order. So one of the methyl group is sent to oxygen, another is trans to oxygen. So both of these methyl groups are non-equivalent, and you have a third. So you see three signals right here. But if you heat it up, what happens when you heat it up? The partial double bond character goes off. You get a lone pair electron back here, and you have a single bond. When you have a single bond, there is a free rotation. So this methyl group and this methyl group can be sent to anti-oxygen, and this is why the broadening of the peaks takes place. And at this particular shift, you see only two peaks, and these two methyl groups merge. Same is in the also. And please have handy this paper, whosoever is going PhD, GOC 1997, because you deal with so many of solvents. When you record your NMR spectrum, you will have unwanted solvent peaks, and you don't know what it is. So if you look at it, you have a chloroform and water. Water in chloroform comes at this position. Acetic acid comes this position. So it varies actually. Okay, so you can look at this paper. The next important concept in NMR is the coupling constant, and I will just try to summarize this in a very concise way. I will not take much time on this. What happens when you do the put your molecule in applied magnetic field? Let us suppose you have HA/HB non-equivalent. So HA has its magnetic moment. So how much magnetic field it will experience will depend on the magnetic moment of HA, but HB is also magnetically active. Okay, so net magnetic moment experienced by HA is magnetic moment of HB plus or minus, can go parallel or opposite. In practice, it does both. So it means your molecule CH resonate that's why remember homotopic protons. Hello, yeah, so homotopic protons don't show coupling. Enantiotopic proton don't show coupling. I talked about diastereotopic protons couples each other. Remember that. So if you don't have HB here, this would be the signal. This is how it would look like. But if you have HB, this is how it is. It will be a doublet. Similarly, this will be a triplet now. So when we talk about a coupling constant, we talk about Kaprlus equation, a dihedral angle. Okay, and dihedral angle, what it is, you all know that. But my simple question is, with one small example that is called fluoroiodoethane. Okay, in this fluoroiodoethane, you have a two triplet. Okay, you have two triplets here. Let us suppose this triplet has a coupling constant of 8 Hertz. What should be the coupling constant here? Look at the literature. 99% times, yes, exactly same. Not only this, if this proton couples to this, if it is 12 Hertz, this is automatically written as a 12 Hertz. That's not correct. That's not correct. Only Kaprlus equation or dihedral angle is not the only factor that affects the coupling constant. There are other factors also. Which are they? Look at it here. Bond length, valence band angle, electronegativity. So if you look at CS3, CS2, X equal to I, BR, CL, F, and this is the coupling constant. So what happens sometimes, you get a correct calculation of coupling constant. Let us suppose in this particular case, you get a correct calculation from your spectra. 8 Hertz, maybe 7.5 Hertz. But since you don't know the reason, you make it incorrect, make it 8 and show your boss and write in the paper and submit. Don't do that. Remember this. Okay. One beautiful question. What it says how will you differentiate cis and trans isomers by NMR? You ask this question to anybody. Before your question is completed, answer will be ready-made. That's the answer. Trans has more coupling constant than cis isomer. This answer is totally incorrect because your answer was based on the assumption that cis and trans isomerism is exhibited only by vinylic system. I will give you another example because my question was open-ended. You have a cyclopropane, this is cis, this is trans. What happens? This is cis stilbene, this is trans stilbene. How will you differentiate those? Again, people will say we can differentiate those by coupling constant. Do the substitution test now. If you do the substitution test, you will get the same compound. These are equivalent protons. Equivalent proton doesn't couple each other. This is the dihedral angle. In case of cis, 6 to 12. In case of trans, 2 to 9. So trans coupling constant in cyclic system is different than the vinylic system. Remember that. So if I take the example of chlorobromoethene, cis and trans, this is how the spectrum looks like. This is trans 14 Hertz. This is cis 9 Hertz. You have a two doublets. Now you have a stilbene. Okay, they don't couple each other. It means you will see a singlet for this, singlet for this. Still, you are asked the question to differentiate this by proton NMR only. Answer is this. This is trans 6.9. This is cis 6.56. Why this so? In case of the trans, the hydrogen is flanked by two of the phenyl ring sterically more hindered. Okay, so steric hindrance means a dispersion effect, and dispersion effect leads to the deshielding, downfield, high delta value, and this is how the NMR looks like. Clean singlet of these two protons in these two. And this is the coupling constant in the cyclic system. What I talk to you, it depends on the nature of X here that can vary. In aromatic system, actually, you can see a triplet. What is the origin of this triplet? Is a non-first order, but it is a clear cut. What is that? I have given you an example of meta-nitrobenzaldehyde. And in this particular case, whenever you are asked such questions, actually, what you should do, you should just try to make things simpler first. In that simpler, let us see, you don't have meta coupling. If you don't have a meta coupling, this HA will be a singlet now. Look at, you have a singlet here. So if you have a singlet here, so this HB will couple with SC, so it is doublet. HT couples with X, it is a doublet. Meta coupling we have ruled out. What about SC? SC couples with B, so 8 Hertz, and that couples with HD, 8 Hertz. So this is 4, this is 4. So it means this composed of 2 lines here. So it is this is how it comes to triplet. One concept what is in spectroscopy actually, non first order and first order spectra, we talk like this. Let us suppose you have a doublet of AX spin system. AX spin system means the signals are far away. Delta V by J is more than 6 or 7. Okay, but if they comes together closer like this, intensity of inner peak increases and outer peak decreases. Right? Now you can ask a question. There can be a situation where the intensity of inner peak increases and outer peak decreases in such a way that the intensity ratio of these 4 peaks is 1:3:3:1, and that's the quartet. So how will you differentiate a quartet and AB double doublet? To do that, if you calculate the coupling constant in case of a quartet, this one, and this one will be same. But in case of a double doublet having 1:3:3:1 intensity ratio, that is first one same, last one is same, the middle is different. So this is a double doublet. So whenever you report the chemical shift, what you do actually? What you do here? You put it here. This is a quartet value for the chemical shift, but we write any of these values, right? And coupling constant is the difference between any of these. Sometimes people, I have seen many places, coupling constant is different between this to this. That's not correct. You can use the NMR for the integration, and that integration can be used for the calculation of the percentage. I have shown here keto-enol tautomerism. Okay, and in that keto-enol tautomerism, the integration value for this keto CH2 is given 12, CH given this. You have to just take out the ratio, and this is what the ratio comes. Higher field strength versus lower field strength. This is at 60 megahertz, this is 300, and this is at 600 megahertz. You can see the shape of the protons. They are the signals, because the chemical shift in hertz is a field dependent, but in delta or ppm, this field independent. This is how you calculate. Let me go and talk to you a little bit about two small problems to show you how to solve those problems. One of the problem, it will have some mass spectrometry data also now in addition to proton. The problem says a diketone, so you are given a nature of the molecule formula is given, and you are given a proton NMR data. MS data, mass data, what it says 100, that is 100%. It is not written M plus. So it cannot be M plus. If you calculate this, it will not be M plus. So this is a dot rank. Now what the question says? The question says which can be obtained by two ways of fragmentation. How will you confirm which fragmentation pathway operates in this compound? Let's try to find out the structure first. If you want to find out the structure, you have a doublet of 6 proton. Doublet of 6 proton can come only when you have an isopropyl group. This one. Okay. Then you have a singlet of 6 proton. Singlet of 6 proton. And you have diketone. So you have a diketone, that's the acetyl 2.3 unit of this. And you have a doublet of 1 proton. Doublet कब आएगा आपका? जब neighboring carbon पे एक hydrogen होगा. So if you hook up all this, this is what the structure is. Now if you look at this structure, this is the alpha carbon, this is a beta carbon, this is gamma, and it can go to this side also, alpha, beta, gamma. So in the mass spectrometry, the unique fragmentation occurs when you have a gamma hydrogen. So that is what we call a McLafferty reagent. So in this molecule, there are possibilities of McLafferty reagent via two ways, one this side, another this side. So it gives you 100. So what is that? So this is the molecule what we talked about. So I read through this structure in which the keto group is given to this side, and this is the hydrogen, okay, gamma hydrogen. So this is how the McLeod rearrangement takes place, and this is 100. Now I push this isopropyl group upward, this acetyl group the downward. This is the gamma hydrogen. This alkene goes off. This is what you get, again 100. Now the question was, which pathway is operating in this fragmentation? This one or that one? How you will control that? You can do that by labeling experiment. What that labeling experiment is, if you use O18 labeled diketo compound, you have one oxygen here, so the molecular weight M by Z will shift to 102. In this case, it will shift to 104. What was the answer? Based on the base peak shifted to M by Z 102, one diketo O18 label was used. So it means what was the fragmentation pattern? This was the fragmentation pattern. Let me move to another beautiful problem. Now, in this case, most of the time, whenever you are asked the questions, you always give your molecular formula. We give you a molecular formula, and that molecular formula, spectral data is given to you. And when spectral data is given to you with that kind of molecular formula, that's the one kind of easiest problem you can think of. Why? Because each of the molecular formula will have n number of isomeric structure you can draw. Okay, so you draw these n number of isomeric structure in the rough base, then correlate your spectral data with those structures, match that, mix match. Okay, based on that you can rule out which structure is incorrect. At the end you will arrive with the correct structure. Now if you look at the Silverstein textbook, in the Silverstein textbook, the most of the problems the later on was given does not have the molecular formula. Okay, they have the spectrum only. You can think it's like that somebody is doing a research on natural product chemistry. You isolate something, it has a solid molecule. Okay, you don't know what it is. You collect your melting point, you collect your IR, NMR, 13C mass, maybe 2D NMR spectra also. Based on that, you have to come to the conclusion what is the molecular formula, and that's real chemistry. So if you understand the spectroscopy class, that will be test only when you can solve those kind of problem. I will give you example here. In this particular case, this is the mass spectrum. No molecular formula is given. Okay, this is the mass spectrum. This is the IR. What mass spectrum says? If you look at this, this is from the Silverstein. This is 262. This is 262. This is 264. So all these cluster of peaks are 2 mass unit apart. Number one. Number two, they have kind of one kind of relationship between their intensity. Whenever you have a mass spectrum, peak with mass unit apart, with some kind of relationship, must think about the presence of halogen, sulfur, and that is important. I will not go to sulfur today. I don't have this much of time, I guess, because it's 12 now. So maybe in 5-7 minutes I will conclude this. So let's see what it is, what this information gives, what information. Now, if you look at this spectrum, it's a beautiful spectrum. 260, 262, 264. It's a multi-halogen compound. Multi-halogen compound में क्या हो सकता है? एक Cl तो नहीं है, क्योंकि M+, M+2, M+4. 2 Cl हो सकते हैं, 2 Br हो सकते हैं, एक Cl, एक Br हो सकते हैं. Okay, look at this. These 120, 224, 226, 1:1. So fragmentation के बाद इसका मतलब इसमें Br है. 198, 200, again Br, again Br, again. That's one. Another information. Look at it here. What is the molecular weight? Even number. Look at the dotted line piece. 1, 2. These two are even. Remember, even molecular weight cannot give you even daughter-ion peak until unless there is a rearrangement in that one. Remember that. So it means these two peaks are coming through a rearrangement taking place in the mass spectrometric conditions. Number two, these two are odd. Even to odd means normal kind of relation. What it is, we'll talk. So now based on this intensity, what is this intensity ratio? This intensity ratio is 1.3, 0.3, and that is a typical for the presence of Cl and Br. Look at it here, IR 1685. You have a carbonyl group attached with a unsaturation. Okay, so by mass spectrum, what we conclude? We conclude that we have Cl and Br, no odd number of nitrogen. Why this so? If you have odd number of nitrogen, your molecular weight would have been odd. Why this so again? Because nitrogen is an element which has even molecular weight, odd valency. So in the periodic table, any other element which has this kind of conformation will obey the nitrogen rule, because organic chemists mostly deal with the nitrogen. This is why we made it a nitrogen rule. Boron gives the same thing. So you have Cl and Br, 260 is the molecular weight. You have a carbonyl. Okay, look at the proton NMR data here. This is the aromatic region. Look at it here. Identical peaks, it's a doublet. So in the aromatic region, two doublets of same height is possible only when you have para-disubstrate system, 1,4 disubstrate system. 1,2 and 1,3 will not give you this. That will give you 3 to 4 line pattern in the aromatic number. Number two, look at in the aliphatic region here. You have a triplet, you have a triplet. When you can get a triplet, you have a CS2 next to each other. Then you will get a triplet. Then you have a pentats, like pentat, whatever. Look at frequency. You have 1, 2, 3.
तो
You
मैं
have
तो उनके
3
लिए ना
CS2.
जो गवर्नमेंट ऑफिशियल है प्रॉपर ना फोन पे आरोग्य सेतु आप में देख के और हमारे पास वो होना चाहिए गवर्नमेंट एम्प्लॉय का जो है एसेंशियल सर्विसेज उसका आई कार्ड होना चाहिए.
Gunjan, turn off your mic. Gunjan, turn off your mic. Turn off your mic, Gunjan. Okay.
अभी तो कुछ नहीं होगा. वैसे कल कोमल का एक वो मेल तो आया है.
So this CH2 is negative. Okay. So it means how many CH2s are here? 1, 2, 3. 3 CH2s you have. 1, 2, 3. How many CH? 1, 2. Symmetrical molecule. This is the quaternary carbon. This is the quaternary carbon. This is the quaternary. So what information you got? So it means this is what I talked to you already. Now use rule 13. What rule 13 says? Divide your molecular weight by 13. Whatever integer value comes, that will be your number of carbon atom. Number of hydrogen will be number of carbon plus remainder if any. Okay. And if you do that, what comes? C20H2. So if you multiply this, the molecular weight becomes 260. But what we have concluded? We said we have a carbonyl group, we have a Cl and we have Br. So what we need to do? We need to add oxygen to it, remove CH4, oxygen is 16, CH4 16. So add oxygen, remove CH4, then add bromine and Cl, remove that much CH2. So what's that? When you add oxygen, remove CH4, this is the molecular formula. Then you have a Cl and Br, which is 144, and 144 molecular formula can come from this fragment. So it means the molecular formula of this compound is C10, H10, BrClO. Calculate the dV now. Well, these are the systematic way of doing things actually. Students make a mistake, they jump. Don't do that. So calculate the dV, you have 5. Aromatic system you have already concluded. Carbonyl you have concluded. So 5 dV is taken care of. So that I already talked. Now in this one, what is the structure now? You have para-disubstrate system. You have CH2, CH2, CH2. You have CO. You have Br. You have Cl. How hook up all these together? right? When you hook up this, you have a structure with you. Do that. Now, these are the three possible structures for this compound. One is this. Another one is this. Swipe the position of Br and Cl, or the acetyl chloride or acetyl bromide also. This somebody can say based on the IR, you can rule it out, because in IR, acetyl chloride will give you the stretching frequency more than 1730 or 1740. Okay, rule out this. How you rule out this? Now people will say, I can, because the Cl is more electronegative than Br, this will be more deshielded. That you can do only when the spectra of both of these compounds is given. But what is in this? A spectra of only one compound is given to you. So how do you know this is more or less? This is where the mass spectrum comes in picture. I will explain that. Let me go one by one. So this is the proposed structure, what I feel it's correct based on the mass spectrum data. So one is, whenever we talk about halogens, it eliminates the HBr-SC. Okay, you have a radical cation there. Removal of HCl gives you this kind of alkene. So neutral molecule, what will be the charge here? Radical cation. So what is this? 224, 226. Br is there. See the intensity. Okay. Next one. Next one is the McLafferty. Look at it. Alpha, beta, gamma. So McLafferty rearrangement. Alkene goes out. This is the fragment. Br is there. What is that? 20, 98, 200. Even. Rearrangement. No fragmentation. Rearrangement. Loss of a neutral molecule. Okay. Then go next. This is the typical fragment for oxonium ion for carbonate. Again, you have bromine there. This one, bromine there. So what is the structure? Character structure is this one. Now you can do the same exercise, put Cl here and Br over here. Your mass spectrum will not satisfy this structure. So this is how you can use the spectroscopic techniques. As I said in the beginning, it's not possible to know each and everything on spectroscopy in 1 hour class. I tried my level best to compile it in such a way that it gives you a complete kind of capsule, so you understand what I meant to say. And another thing is, as I said in the beginning, it's really difficult to deliver a talk in this kind of way, because when you don't have anybody in front listening to you. Okay, so we go to the class and we talk. We have so many students looking at the audience. We can judge whether the lecture is being appreciated or not. In this case, we don't know. We are just talking and you are just listening somewhere. But I tried my level best. Let me go to next slide. Anybody who is interested, I have developed 3 YouTube lectures recently. This is during the lockdown period. This is how I utilize my time. Okay, I have been working 10-12 hours per day just reading the spectroscopy, right? Nothing else, because I have a passion on that. And mass spectrometry, YouTube is there. Problem based on NMR and mass, there are 2 other YouTubes. And let me give you one statistics. In the NET examination 2018, only 17% students attempted the spectroscopy related problems, and only 3% were correct. And as I said, the chemistry, what we need in the spectroscopy is 10+2 class chemistry. Yet we make a mistake. Because we make a mistake because we don't understand it properly. Okay, so do it, and if you have any questions and queries, I will try to solve it here also, and you can ask me sometime later. And this is what my scientific lineage comes from, who are my ancestors in my field. I did my PhD with Dr. D.S. Bhakuni from Center for Research Institute, Lucknow. He did PhD with Professor Derek Barton, the Nobel laureate, and Barton did PhD with Hellborn Punch. I go down like this. It goes to Berzelius, Uppsala, then goes to Benjet Fernand, 1751. And I did a postdoc with Richard Gibbs. Richard Gibbs did a PhD with Okamara with Kurtz with Woodward, the Nobel laureate. Woodward did with Norris with Vincent is sitting, Limchard, Euler, urea free, Gamlin. Look at it. This is the UK side. This is the United States side. The end point is one. इन सबका forefather एक ही निकले वो उपसाला यूनिवर्सिटी. Another postdoc I did from Indiana University, Bloomington with Jeff Jeloski. I could trace his lineage up to 1637. So this is what my scientific lineage is, and this is what we do. We work on primarily on medicinal chemistry, but recently we started working on nanocatalysis also. Many of those papers were highlighted by Singlet and appeared on the cover page of the journal. And I thank again to Rohit and Dr. Professor Singh for giving me this wonderful opportunity. Though in my office AC is not working, for about 2 hours I have been sitting on this, and I'm really enjoying. Unfortunately, I can't see the audience. That's the only problem. And thank you very much for patience. Thank you. And now you can ask the question if you have.
Sir, thank you very much, sir. And I am really thankful for your support and giving us this lecture. Sir, are you there?
Yes, please, yes.
Yeah. So, sir, I think the audiences will agree with me that actually these type of problems are the main problems. Actually, when we see the competitive exams, which include the NET, GATE, and others, the simple problems are not there. These type of complex issues are there, which are actually exceptional issues. So I think in that way it was a very well compiled presentation, and we will be putting it on YouTube with your permission, sir. And we will be circulating it with our students in chemistry department, Punjab University. And those who want to have the link, they can write to me at my email ID, which is given down in the bottom of the pamphlet also, and in the chat section also. So that will be available for all to see. And of course, Professor Rawat can also upload it. It's on his YouTube channel. He has a very dynamic YouTube slides and YouTube presentations. And I mean, looking at that, actually, I was inspired to invite Professor Rawat, and I'm delighted that, sir, you have given a very remarkable talk. So thank you very much. And with this, I think I'll open the session for queries. And there were till the time you raise hands, there were a couple of questions that came in, and there was a question from Gurpreet, which stated that you talk about the effect of solvents and the ideal. So, what is the ideal condition for NMR spectrum? Which, yeah. So she was talking. Yeah.
Her question is the choice of solvent.
Her question is the ideal condition for NMR experimentations for solvent as well as other.
Yeah, there is nothing called the ideal condition. The only thing is the compound must be good soluble in the solvent in which you want to record your NMR spectra. It should not precipitate out during the experiment. So the solubility should be. That's the only requirement.
The specific question was ideal conditions for NMR sample preparation.
Yes. Number one, there should not any of foreign particles like cotton beads. Sometimes you filter it from the cotton. There should not be any fiber in it. Number one. Number two, the compound should not be concentrated. It's a 10 molar solution is good enough for your proton NMR. So you should not record proton NMR and carbon NMR by a same sample. When you do that, it means you will make a concentrated solution, and that will affect your shape of your proton NMR due to the longer T1 and T2.
Okay. So there was another comment. I think it is. I mean, sir, one of the comments that comes is from Dr. BMS Bisht. He says, one of the excellent scientific lectures I've heard. Thanks, Professor Rawat, for providing valuable knowledge and information. Thanks for providing such a brilliant webinar. the description on toposity was brilliant. So this is just a comment. I thought it's a question. So
Thanks.
So as you were saying that you don't know the feedback, so I'm just providing the feedback also with.
Thank you. Thank you, sir.
Yeah. So there was a question from Bunty Sharma. Thank you for a wonderful talk. I have a query. How metal and metal magnetism affect the compound NMR?
Yes, the best, because we don't deal with metals as organic chemists. That's the biggest problem. But the best example is the copper 1 and copper 2. Okay, if you make a copper 1 complex of your molecule, it must be under inert atmosphere. Only then you will be able to record the NMR spectrum. Otherwise, the paramagnetism due to the copper 2 will affect your spectrum. All the spectrum peaks will be very broad. So the paramagnetism affects the quality of the spectrum to the greater extent.
Okay.
For that, you can use the EPR.
Okay. It is open. You can ask your questions directly also. You can just raise your hands and I will unmute your mics and you can ask the question directly also. So it is anyone who wants to ask a question can raise a hand. There is an option there to raise the hand. And there was a comment from, in the meantime, I'll just let you know.
So how many participants total there?
Sir, we were having a maximum at one time was 110. So far there are 97 still there. And actually this was a meeting which was restricted to 100 participants.
I see.
Yeah. So anyways, I have informed, some of them actually contacted me during the meeting also. I have informed that we will be providing the YouTube link. And so we were having 110 at one time, which was a maximum.
Okay.
Yeah. So actually, I was told that maybe we will have 200, but seems that it was also limited to 100. Yeah. So there was a comment from Dr. Muhammad Abid. He said, I would suggest to have some more sessions by Professor Rawat, sir, on problem solving as well as 2D NMR. So, sir, some demands are coming in. So,
yeah. Okay, thank you.
There are many comments. You can go to the chat section. There are a lot of comments, but I am not finding questions in between them. There are more like appreciative comments. And anyone who wants to come in and ask question, yeah, there is a question from Neha Garg. I'll unmute her. Yeah, it is unmuted. Yes.
Hello. Good afternoon, sir.
Yeah, good afternoon.
Sir, the shielding and deshielding effect of the cyclopropane ring is how to understand with the help of sigma electrons of the CH2 or how?
Yes, actually, when you this is that's not well explained actually. But if you draw the the cone, this shielding deshielding cone,
Yes.
like you draw for cyclohexane system.
Okay.
In a similar way, if you draw that cone, you will understand which region is the shielded one and which one is the shielded region.
Okay. Thank you, sir. Thank you.
So there is a hand raised from Divya P. Johnny. I think it is raised for a long time. Is Dia P. Johnny. Is Dia there? Hello. I think this was raised earlier, so probably she doesn't want to ask the question. Anyone who wants to ask the question? And so there are queries regarding, can we have the PDF of the presentation and other stuff, so we can actually they can have the YouTube link. I
think better with the YouTube, they can watch this many times.
Yes.
If anything, they will understand better.
Yes. So we shall be providing the YouTube link to all the chemistry students of Punjab University through email from the official Punjab University ID. All others can just send me an email. Once it is uploaded on YouTube, we'll send you the link. So that is the way we'll go about this. Sir, I think probably there might be students asking, but maybe they can have your email ID. They can contact you directly also. So the email
Oh, yes, yes, no problem.
Yeah, so you can go to the University of Delhi's web link also, and I can provide you the email ID also of Professor Rawat. Yeah, just a minute. Sir, you can just spell out your email ID for the students if it is possible.
Acha, my email ID, that is Diwan S. Rawat, DIWAN SRAWAT
Yeah, that's right. So you can directly write to Professor Rawat, you can write to me, and then you will be provided with the link and other information. Sir, are you there? Hello? I think probably we might have lost. Sir, are you there? So with this, I would request Professor Singh. Yeah. I will request Professor K.N. Singh.
Yes.
Yeah.
No, yes.
Hello?
Yeah, sir.
Hello?
Yeah, Professor Singh, I would request you to kindly formally thank Professor Rawat for this wonderful lecture.
Rohit, can you hear me?
Yes, sir, we can hear you, sir. Although we can't see you, but we can hear you, yes.
Okay. I, on behalf of the students and the faculty of the chemistry department, Punjab University, Chandigarh, extend a very hearty vote of thanks to Professor Rawat for sparing the time from his busy schedule and accept for this very informative talk and covering many areas of NMR spectroscopy, which will be very useful to the students as well as the research scholars. I would also thank Dr. Rohit for organizing this chemistry webinar and making this event as a grand success. Thank you very much, sir. Thank you very much again.
Thank you, sir, and thanks a lot for your support.
Thank you, sir.
Yeah, and we hope that students also liked it, and we'll try our best to put more webinar series on topics which are related to students in future also. Thank you very much. Thanks a lot, all. Thank you, sir. Thank you so much. I'll be here. Thanks a lot. Thank you.
Thank you, sir.
Yeah. So the video.